Thank you.
It started. I'm not seeing, oh wait, never mind. One sec. Can you see my screen? Great. Hello, my name is Ruxin Li. Today I'll be talking about interpreting dialogue models through local explanation methods. As AI assistants become more commonplace, it will become important to understand and trust their decisions. Neural models such as GPT-2 facilitates the development of open domain chatbots that behave like black boxes and are difficult to explain their complex behavior. Techniques such as localized. I'm sorry, can you guys see my screen? Or is it black screen? Hello?
We can see your screen.
Okay, sorry. I couldn't see, so never mind. Techniques such as localized interpretation of response generation aim to improve model transparency by extracting key input-output interactions that affects prediction. My motivation for this research was to gain hands-on experience in using interpretation techniques to explain patterns of neural discourse. LERC stands for Local Explanation of Dialogue Response Generation. It is a technique specifically designed to explain the internal reasoning of a neural dialogue model to increase the transparency of the prediction process. At a high level, LERC works by identifying significant interactions between input segments, such as user words, and output segments, such as chatbot replies, and determining which input-output relationship are the most relevant to the internal logic of the model. I re-implemented key components of LERC in PyTorch. This included first fine-tuning a GPT-2 model on the daily dialogue dataset to create a conversational agent. Then I wanted to see how the explanation would differ for a more task-oriented dialogue genre. So I utilized a new TOD simulators dataset based on chatbot testing tool conversations and pre-processed it into the proper format. With my dialogue model and test sets ready, I ran LERC to extract explanations on both daily dialogue and TOD simulators and evaluated the results using metrics like perplexity and loss, as well as visual heat maps for input-output interactions. I also implemented new variation of the LERC loss functions to understand how changing optimization impacts explanation quality. One new version I added was LERC sharp mean, which computes the mean of raw probability differences rather than using the differences directly. Taking the mean can help address potential limitation by reducing skew from outlier predictions. Throughout this all-around evaluation approach, I sought answers to key questions. Can LERC accurately capture the salient reasoning of dialogue models? How does the purpose and genre of conversation influence the quality of explanations? And critically, do the new loss formulations I implemented lead to enhanced results? The results demonstrate that LERC can successfully extract meaningful explanations between input and response tokens on the daily dialogue dataset. This aligns with my expectations and validates LERC's ability to interpret open domain conversation models. However, when applied to the task-oriented TOD simulator dataset, LERC produces weaker and less relevant explanations, as shown in the figure where gasoline is oddly linked to hot and potato. This negative result indicates that LERC is better suited for chit-chat dialogues compared to goal-oriented ones, confirming my hypothesis that explanation models need customization for different dialogue genres. Meanwhile, the new LERC-Huber and LERC-Sharp-Mean loss variation did not lead to significant observable differences in explanation quality based on the heat map visualizations. This fails to validate my hypothesis that they could improve performances and suggest that the original LERC losses are reasonable. In summary, the results showcase the potential of LERC in interpreting neural chatbot models. However, they also reveal certain limitations when explaining more task-oriented dialogues. This finding implied that adopting hybrid approaches may be necessary for comprehensive and reliable explanation across various dialogue genres. Nevertheless, it's important to note that LERC provides a robust foundation to further develop and refine our understanding. Thank you for listening. I believe we can move on to the discussion question.
Yeah, so first question. So I'm curious to learn more about how you envision blending local and global explanations in those hybrid methods you mentioned. So could you expand that idea?
Absolutely. So one intuitive approach is like a hierarchical setup where first, a high-level module identifies most important dialogue segments using holistic reasoning chains it extracts. Then we use a lower-level component zooms in to get refined words links between input and responses within those salient segments. The local explainer almost operates in targeted region, the global module spotlights as relevant. And another idea is parallel local and global explainers. We can then blend their importance scores per dialogue except to get a consolidated relevance. In both cases, it's a fusing detailed input-output interactions between the bigger context picture to get multifaceted interactions. There seem to be promising ways to combine precision of local and coverage of global through joint or modular modeling. I hope that explains.
Yeah, that's good. And the second question is, you pointed out how dialogue genre impacts explanation quality and customization helps. Could you elaborate on why that genre-specific customization is so essential?
Yeah, for sure. Conversations have really different flavor based on the genre. Like open-ended chit-chat permits way more diverse responses versus task-oriented dialogues centered on specific objectives. We saw that Lurk's word linking shines for chit-chat, but falls short for interprets complex, goal-driven dialogues. So techniques tailored to particular genres can take into account special challenges that get overlooked by one-size-fits-all methods. Specialization allows targeting precise reasoning fingerprints to each dialogue type. So this custom fit enables tapping unique structures for superior quality, kind of like a bespoke suit versus off the check.
Great. Then what ideas do you have for enhancing the lyric loss formulation to reduce noise and better capture salient signals?
I believe rather than raw probability differences or just the mean, advanced probability aggregation over the distribution seem promising to spotlight strong signals. Like for instance, weighing high confidence examples more when computing relevance scores or applying nonlinear functions beyond the mean to smooth noise and skew. More analysis on simulated dialogues could reveal optimal formulations for accurately accessing explanation relevance, but overall, lots of potential to isolate salient signals from the probability space through smart aggregation, I think.
Cool. And what future research direction do you find promising for interpretable dialogue AI based on your findings?
A key direction seems to be fusing together local word level explanations like we saw it with LERG, with more holistic dialogue level features to get comprehensive interpretations across genres. Things like capturing long-term reasoning chains are going to be vital for goal-driven conversations. Maybe hierarchical models that first globally analyze the local zero in could work. Um, or aggregated score from parallel local and global explainers per accept. However, it's combined blending granularly input-output links with bigger structures seem key for multi-phase explanations. And advancing evaluation framework to directly gauge human interpretability around like what constitutes satisfactory explanations will further mature the field.
Okay, so last question. Why is transparency in conversational AI systems important? And how can improve the explainability facilitate adoption?
Certainly. As advanced dialogue agents spread to sensitive domains like healthcare, explainability grows crucial for monitoring potential reliability issue or biases. Improved transparency really assures proper understanding of model behaviors by various user groups. It builds trust by surfacing unfairness or unreliability early to address concerns. Explanation acts as guardrails against unintended impact. For risk-averse institution debating deploying this technology, I think model interpretability helps validate safe, ethical usage and providing the guarantees against harms. So systematically, transparency will not doubt like accelerates adoption by clearing the confidence bar.
Thank you.
Thank you for listening. We can move on to the next presentation.
All right, I will share my screen. All right. Hello, everyone. My name is Clark Liao, and I'm going to describe my term paper called How to Improve Domain Generalization and its Application. So domain generalization is an idea that incorporates knowledge from multiple source domains into a single model that could generalize well on unseen target domains. And this is a challenging and significant topic in machine learning because it is capable of enhancing model performance across various domains. So first in the paper, I described the drawbacks and challenges the old methods had. Then the main paper I reviewed proposed a framework called Domain Bed, which integrates multiple data sets, baseline algorithm, and model selection criteria to improve the performance of domain generalization. So in order to verify the rationality and authenticity of domain bed, I implemented new experience use rotated MNIST, which is one of the most popular data sets normally used in machine learning. In reviewing the related work, one introduces biases in data sets and propose solution on reducing the impact of biases to the model generalizations. The other one described the application of domain generalization in the field of data augmentation for medical 3D images. It finds that deep stack transformations method for domain generalization, which improved the segmentation performances on unseen domains and the ability of domain generalization. And back to the main paper, the authors proposed solution involved the use of empirical risk minimization, or ERM, along with modern neural network architecture and data augmentation techniques. I re-implemented the rotated MNIST experiment by comparing the ERM with the interactive genetic algorithm, or IGA. I verified that the performance of ERM algorithm indeed overcame others. So the key finding of this paper is that the ERM consistently outperforms other algorithms in model selection and domain generalization tasks. However, the results from either my experience or the authors might not always be true because the existence of biased datasets. So in conclusion, the findings offer new insight to domain generalization in machine learning, they underline the need for ongoing research in this field, especially considering the involving nature of data sets and machine learning applications. But like I mentioned from previous slide, the theories are not solid. Many more experiments should be done in order to actually improve the performance of domain generalization. Other than that, to improve the performance, it is also necessary to improve modern neural network architectures. Therefore, much more efforts to do on this. So this is my references and
Yeah, very great.
questions.
So I got several questions on this. The
Yeah.
first one, how does the domain-based framework contribute to the field of domain generalization in machine learning?
Okay, so domain BAD is a significant contribution as it consolidates various domain generalization datasets and algorithm into a single unified testing framework. And this standardization allows researchers to test, compare the efficiency of different domain generalization approaches under a consistent set of conditions. The framework also includes datasets with inherent domain shifts, a suite of popular data domain generalization algorithm, and a standardized protocol for training and validation that emphasize the importance of algorithm selection based on validation on separate domain. And by providing this benchmark, DomainBet enables more transparent and equitable comparisons between methods and driven the field towards more robust solution for this field.
Okay, and my second one is that what were the key findings when comparing empirical risk minimization with the interactive genetic algorithm using the rotated MNIST datasets?
Yeah, when I was evaluating the rotated MNIST dataset, the paper found that ERM consistently achieved lower loss, and higher accuracy compared to IGA. And this finding suggests that even though IGA is designed to handle multiple tasks by evolving the population of neural network, ERM's straightforward approach of minimizing average training error across all domains is more effective. This could be due to ERM's ability to leverage modern neural network architecture that are highly expressive and can benefit from extensive data organization. And ERM's simplicity and the use of powerful neural networks seem to give it an edge over the more complex IGA for domain generalization in this context.
And can you also explain the significance of the paper's claim that the choice of evaluation protocol heavily influences the perceived performance of domain generalization algorithms?
Yeah, sure. The paper's claim points to a critical aspect of machine learning research is the consistency and reliability of evaluation matrix. Without a standardized protocol, comparison between algorithm can be unfair or misleading. For example, an algorithm might appear to perform well on one data set or under a particular set of conditions, but fail to generalize across broader or different data sets. And the domain-based framework addresses this issue by offering a standardized evaluation protocol, which includes predefined train or validation splits and a recommendation to select hyperparameters based on performance on a validation domain that is distinct from the test domains. And this approach ensures that the reported performance is reflective of an algorithm ability to generalize, not just its capacity to fit the peculiarities of a specific data set or evaluation setup. Do we have
Okay,
to?
we don't have time, so
Yeah, so.
Yeah.
Right, thank you.
thank you.
Hi guys. Today I'm going to talk about the Ghost model, a model that can make the convolution neural network to be more efficient. Okay, so deep convolutional neural network has shown excellent performance on computer vision related tasks like image recognition, object detection, and so on. However, convolutional neural networks requires a very large number of parameters and floating point operations. For a CNN model, we can not only like train them and test them, we actually need to use them. But it's challenging to deploy CNN models on some memory and computational source limited devices like mobile phones, self-driving cars due to its high cost. So if there's a way to make the model more efficient, okay, so before talking the Ghost model, I wanted to mention the feature maps first. We all know that the feature maps are outputs of CNN layer. It can represent the specific features of input or some spatial information of input. They're very important. However, there are some redundancy in feature maps produced by same CNN layers. Like the figure I showed on left, some feature maps are really similar. However, even though they are similar, we still need memory and computational source to generate them. So Ghost model is used to deal with this problem. The Ghost model is introduced to address redundancy in feature maps generated by traditional CNNs. Instead of directly producing all feature maps with high computational cost, the model generates a smaller set of primary feature maps by using original expensive operations. These are then transformed using lightweight linear operations to create ghost feature maps. This method offers similar outputs with reduced computational overhead, capitalizing on the inherent redundancy of traditional neural architectures to maintain performance will be more self-sufficient. For instance, consider the convolutional layer producing n feature maps. Instead of generating all n maps directly, the Ghost model first produces a smaller set of m primary feature maps. And then each of these primary feature maps are then transformed by using a series of cheap linear operations to produce multiple ghost feature maps. And then the combination of primary and ghost feature maps results in the desired n feature maps. Okay, for experiment, Cipher10 is used to train and test the model, and depth-wise convolution, it shows to be the cheap operation. Two models used to compare are VG16 and Ghost VG16. The Ghost VG16 is the model that all convolutional layers in VG16 are replaced by the Ghost model. Here's the result. We can see that the accuracy only has a very slight drop from 86% to 85%, but total params and flows and total sets has a 50% drop. The params dropped from 15 million to 7 million, and total sets dropped from 62 MB to 3 MB. All those improved makes it become more deployable on memory and computational source limited devices. And here's the feature maps generated by both model. Although the similar feature maps is indeed generated, but the feature maps generated by the Ghost model are, you can see, the darker than those generated by normal CNN layer. So in conclusion, Ghost model can actually have a huge improvement on efficiency and convolutional networks model with a slight accuracy drop, but it will produce a darker feature map that may indicate a weaker ability of capturing the features of the input. Okay, so any questions?
Yeah, so you mentioned the decrease of parameters. Do you have any idea of how much it improves the training time or computational power consumption?
Okay, it's a good question. But I want to say that the ghost model is not designed to like reduce the training time of neural networks. Although it can indeed reduce the training time because the parameters need to be trained are reduced significantly, and since the floating point operations are also reduced significantly, the computational power consumption also reduced. I want to say that the ghost model is designed to make the CNNs more deployable on embedded devices, since all those devices has limited computational resources. And for how ghost model can improve the consumption, I want to give you an example. So suppose we want to generate 100 feature maps. If we first generate 50 prime maps and then generate 50 ghost maps, the cost will only be 1/2. And if we first generate 25 prime feature maps and then generate 75 ghost maps, the cost will be only 1/4. But we need to remember that like the less primary maps we generate, the lower accuracy will be. Yeah.
Okay. So can the ghost model modification be implemented on like any of the CNN or if it's architecture specific?
Okay, so although the name of ghost model is ghost model, but it actually more like a redesign of convolutional layers. So actually you can replace all convolutional layers in all CNN networks with the ghost model. Yeah, and then the ghost model will produce the same number of feature maps, same height, same width as original convolutional layers, but with a lower cost.
Okay, so I see you only show the result of VGG result. Do you have any other performance comparison for other CN with without ghost model layers?
Okay, so unfortunately, my answer is no, because I only did the experiment by using the VG16 architectures. Since I do not have like a super devices, I only test the ghost model on some simple architectures using a simple data set like Cipher10. But in the original paper, the author did the experiment with different scene architectures, and ghost model performs really well.
Okay,
Yeah.
so it achieves a comparable result with only like a half numbers of the parameters. Does that mean the scale of the model doesn't really matter?
Okay. I think it really depends on the purpose of scene. If you want to deploy the scene on embedded systems, and you can actually accept some accuracy drop, then I think the scale of the model really doesn't matter. But if you want the accuracy, and yeah, I would like to say the scale does matter. So when the scale get larger, the model can actually learn more things, right?
All right, yeah. So the next question is more tricky. So do you still think the ghost model is still CNN or it's something else?
Uh, okay. As I said before, like ghost model is kind of a layer instead of whole networks. So yeah, but if a network is all based on ghost model, I would like to say that it is still a CNN. Yeah.
Okay, cool. Thank you.
Okay. So thank you, question.
Okay. Hi, my name is Yun Hao. So my presentation is about the extended experiment with group-dependent label noise. Next slide. Okay, with the progressively wide usage of machine learning in assisting humans to make decisions, people have raised concerns about fairness of the algorithm in real life. For a long time, people brought out different algorithms enforcing the fairness metrics. However, recently label noise was found to be degenerative to the performance of fairness algorithms. Fortunately, the surrogate loss algorithm was proposed to be resistant to this noise. However, the original paper does not extensively compare its performance with other fairness algorithms on a real-world dataset with continuous noise rates. And this motivates me to manually conduct an extended experiment to test the performance of the surrogate loss algorithm on a real-world dataset at different noise levels. And to be more confident on the performance of the algorithm, comparison between 3 other different fairness algorithms is also included. And the first part of the implementation is the noisy generator. In this experiment, noise was generated in the IDAL dataset based on the group attribute size and the label income. Here, the noise rate is defined by the conditional probability in the first 2 equations. In the experiment, it is manually decided constant between 0 and 1, representing the proportion of lived samples in a certain group with a certain label. And the surrogate loss approach aims to substitute the loss function of the comparison algorithm with the surrogate loss function, which is defined by the listed 2 equations. Thus, the experiment manually implements the logistic regression and then substitute its loss function with the surrogate loss. And this table shows the implementation results. Abbreviation is listed besides the table. And in the table, cell is marked in green to represent that the corresponding algorithm has the best performance compared with other 4 algorithms. And similarly, the worst one is marked in red. The following interpretation can be drawn by observing this table. So the first observation is that blindly imposing fairness on classifiers in noisy dataset will cause loss in accuracy. From the table, one can observe that EOP always has lower accuracy than LR in all label noise. In all noisy rates. For instance, when the noise rate is 0, EOP has an average accuracy of 0.5547, which is significantly lower than that of the LR, which is 0.713. This also holds for all other classifiers other than the surrogate loss. And the second observation is that surrogate loss approach has overall higher accuracy compared with other algorithms, according to highlighted green cell in column of the accuracy. One can observe that the surrogate loss has the highest accuracy among all the noisy rates except for 0.2. And this holds for my second observation. And the third one can be found by comparing the accuracy loss of surrogate loss approach with those of other algorithms with the noise rate increased by arbitrary amount. According to the red cell in the DP and EOD columns, we can observe that the surrogate loss has bad performance in the group-dependent label noise compared with other algorithms. As both DP and EOD are fairness metrics, and the surrogates also get a worse value. And this will support my final observation. The take-home message is the first, blindly imposing fairness on classifiers in noisy dataset will cause loss in accuracy. And the second one is that surrogate loss approach is more resistant to group-dependent label noise and overall achieves higher accuracy compared with other fairness algorithms. And thank you for watching. Is there any question?
Yes, my first question is that, do you know what causes surrogate loss to have bad fairness performances in the group-dependent noise compared with other algorithms?
Okay, the surrogate loss, according to my previous slide's definition, itself does conditional label flipping when calculating the loss function. And this might suggest that it is doing the inverse process of the group-dependent label noise generation when calculating it. And this loss function might give the correct direction for accuracy, but not necessary for the fairness metric. And however, this is only a very preliminary analysis of the observation. And further study is needed to confidently bring out the formal explanation.
Great. Can you be more specific about how you generate noise on ADULT datasets?
Okay, I can provide an example to explain this. Well, suppose that 0.3 noise rate is imposed on the samples in the female group with a salary higher than $50,000. And the number of samples that meet this requirement is 1,000 people. Then 3,000 people, the 300 people in female group with a salary higher than 50K will be changed to have a salary lower or equal to 50K. And knowing that idle dataset has an inherent noisy rate of 0.38, the noise ranging from 0 to 0.5 were generated and then tested in this experiment.
How did you get the conclusion that surrogate loss approach is more resistant to the group-dependent noise inaccuracy than other algorithms, which is your third conclusion?
So this conclusion can be drawn by comparing the accuracy loss of surrogate loss approach with those of other algorithms when the noisy rate increases by an arbitrary amount. For example, when the noisy level increases from 0.0 to 0.5, the LR's average accuracy, here we can see that is going from 0.7813 and then increase to 0.7500. And in comparison, the surrogate loss decrease from 0.7920 to 0.7854. So this is significantly lower than that of LR. So we can support the third conclusion.
Why did you choose RW, PR, and EOP as the three algorithms to be compared with the surrogate loss approach?
Okay, first, they are algorithms enforcing fairness without being aware of label noise. So they are expected to have worse performance than the proposed surrogate loss approach. And to ensure that the chosen three fairness algorithms are representative, pre-processing, in-processing, and post-processing algorithm are separately chosen to compare with it. In other words, the reweighting is a pre-processing algorithm, and the prejudice remover is in-processing, and the EOP is a post-processing fairness algorithm. They are chosen to be representative. Yeah.
My last question is, what is your testing logistics? For example, like how many trials you run for each case, and how did you get this table?
Okay, idle dataset is first imported and then modified by noise generator, and then the noisy dataset is then pre-processed by doing normalization and train test splitting. And the chosen three fairness algorithm together with logistic regression and the surrogate loss approach are then trained and tested using per-processed data. And the idle dataset is then imposed 6 different noisy rates. They are 0, 0.1, 0.2, and all the way count to 0.5. And for each noisy rate, 10 trials are run with the metric of accuracy, DP, and EOD. And finally, the average and standard deviation among the 10 trials are calculated and displayed in the experiment result.
Thank you for your answers.
Yeah, thank you.
Hi, so I'm going to talk about a differentiable Selmas augmentation data condensation. So first, we will have a look at the data sets we are using today. For example, Cefaten has 60,000 images, and Minist also has like 70,000 images. For general purpose data sets, it is even larger. ImageNet has 1,000 objects, which is 150 gigabytes in total. It is not only make it hard to share the dataset, but also it consumes plenty of computational power. This problem is more serious for deep networks. So in addition to improving the architecture of models, we may also reduce the size of training sets while still maintaining a comparable performance. The state-of-the-art methodologies divide in 3 directions. We'll talk about the the third one, data condensation today, and the extension I proposed involves call set selection. The idea of data condensation is to synthesize a training set S, and we have original set T. The model trained by both sets should have similar parameters. Since we do not know the parameters during the synthesis, we assume they are finally the same. And we want to minimize the distance, here D, between the gradients of losses produced by those 2 sets. So problem is formulated as this equation. The novel feature of DSA is to introduce the augmentation, such as cropping, rotation, and cover jittering for images. The problem formulation upgrades to the new form here. One thing we have to care about is that the augmentation method should be differentiable, thus we can back propagate the loss. The evaluation shows the auto performance of DSA related to cause selection as other set synthesized methods. Only the basic data concentration method can perform well or perform better than DSA in the very low compression rate situations. The evaluation also shows that there's no globally optimal augmentation options unless you use a combination of all these augmentation methodologies. By combination, it means you randomly choose one of them for each epoch. Since the process of data synthesis is time-consuming, even more time-consuming than training the model, I sought to an opportunity to accelerate this process. Then I noticed that the initialization strategy played a significant role. Thus, I proposed a initialization strategy that utilizes the cause selection, which we mentioned as the first reaction of the dataset reduction. The idea is to include more correct cases in the initial set. This is maximizing the sum of norms of each sampled images minus the mean, which is formulated as equation here. So we first look at the CIFAR-10 result without the extension. It's just a reproduction of the result in the paper. As we can see, even after 10 hours, it can achieve a very poor performance. As a suggested iteration by the authors, it might take like 20 hours to get a well-performed result. Then I compare the extended strategy with the author's method's random sampling, which is at the right. The left one in figure 2, which is the extended method, contains more hard to recognize figures, like the first of 8 as not of 0. There are many more examples. After the same number of iterations at time, the one with the extended strategy shows a better performance. And I also recorded the performance of both initialization strategy at each 25 iterations. It shows like after the 150 iterations, the extended one start to converge, but the random one does not. You can see the drop over here, a drop over here, and a drop over here for the random one and the extended one. After the 150 iterations, it starts. Well, it still keep going up. So in conclusion, even if with the DSA, it takes like 2 hours to condense a very small data set, and so the process is still time consuming. However, I also prove that DSA is one of that can achieve the best performance among all the options. All right, that's all.
Okay, so I have several questions for you.
Mhm.
In your extended method, you talk about the corner cases. So how do you determine what is a corner case?
So by corner case, I mean that is farthest away from the mean of the class. So although I formulate this as a maximization problem, but indeed it's just a sorting problem because you know the mean and you just sort them by their difference to the mean or norm of difference to the mean.
Okay, so and how can you ensure that different architectures can have acceptable accuracy by using your condensed training data?
It's actually not guaranteed because the performance of the training, the training performance of a neural network is upper bounded by the original set. The condensed data set cannot outperform the original set. So if you train the neural network with a very poor, very bad data set, even if you condense it, maybe it's much quicker to train it, but the performance is still pretty bad. So there's no guarantee.
Okay, so we know that on the model training process, we might stuck into local minimum. So what if your condensed data is generated based on the local minimum?
Right. So for image synthesis, it's really hard to find to have a local minimal because you have to go through this optimization problems like for many iterations, and there's another problem is there's another situation that because of the optimization I mentioned here, you want to minimize the gradient of the loss, and you know that the minimum value of gradient of loss is 0. And even if you find out your gradient, the distance between the gradient and loss is converged to a very high value, you can adjust your like momentum or something to make it close to 0. Then you know that it's a global minimum because you know the global minimum is 0.
Okay, so how's your result compared to other methods that can reduce the train data set?
Of course, DSA or any data condensation method with or without any extension can overperform the course selection or even GANs. But DSA is the one that has the best performance if you don't want to say, okay, I only want 1 images in a class. If you want to say I want to more than 10 images in a class, then DSA is the best choice for now.
Okay, so and you said that we need a really long time to condense the data set. Do you think it is worthwhile to condense data but finally achieve a lower accuracy rate?
It really depends on the goals. If you want to synthesize a data set that can be reused multiple times, say I want to use this data set to train like thousands of models, then of course it's worse since you spend like 20 hours to synthesize a data set, but for each training you may reduce the training set by like 1 hour, 2 hours, 4 hours. But you have to reduce it, but you reduce this like 10,000 times, then it's totally worse.
Okay, so that's my questions. Thank you so
All
much.
right, thank you.
Do I start the recording right now or do I wait to the end of the class?
Well, I think you can stop recording now, and you are all good to go now.
Thank you. Great
Thank
day.
you.